All right. Hello, everybody. In this video, I'm going to be talking about the mean value theorem. So this is a really cool tool that we have, just like as a mathematician in calculus. You'll be seeing this a lot, especially if you're in calculus and you're studying for the AP exam. Uh, just like in my practices, in my personal experience, I'm pretty sure I've seen at least one mean value theorem question uh, in each exam. So this is really something you want to know, and besides the fact that it's important for the exam, it's also really cool to just know and understand at a basic level. So anyway, what is the mean value theorem? Well, it's kind of a proof that relates the derivative of a function at a point, so the instantaneous rate of change, and an average rate of change. So I'll explain what I mean in a second. So right here, I've graphed this function. It's just f of x is equal to x to the third minus 2x squared. And I've graphed it on Desmos over here, just so we can kind of get a grasp of how this behaves, what it looks like, what we can expect from it. So just to start, I'm hoping that you guys have you're already familiar with average rates of change. Average rates of change. So what I want to know is I want to find the average rate of change just for this example in between over the interval 1 and 3. So that would be from, I'm pretty sure it would be here, over here, all the way to over here. So to find this average rate of change, I'm just going to write average rate of change. Okay, so this is going to be the change in y, which I can describe as f of 3 minus f of 1, and then I'm going to divide that by change in x. So, oh, this would be 1 over here. Okay, so what I'm going to do is I'm going to evaluate this function just at these values. So at 3, that's going to give me 3 to the third. That's going to be 27. So that'll be 27. I'll write f of 3. This will be equal to 27 minus 3 squared is 9 times 2 will be 18. So it looks like we'll have 27 minus 18, which will be equal to 9. And you know what? Let's actually double check. So this is x is equal to 3 right here. And if we go all the way up, sure enough, it looks like we hit just barely 9 over here. So, okay. So we now know f of 3, so this will be 9. Okay, so now let's find f of 1. So we can either look at the graph or we can evaluate it algebraically. I'm going to do both just for funsies. So 1 to the third power is just 1. 1 squared. 1 squared is just 1, so this will be 1 minus 2. Alright, so this will give us negative 1. So, and you know what? That adds up, because if this is x is equal to 1, and sure enough, y is equal to negative 1 here. So, I'm going to remember I'm subtracting here, so I'm subtracting a negative. I'm just going to write it like that just so I don't get mixed up. And 3 minus 2 is, 3 minus 1 is 2. I got things all wonky. So I'm just going to continue writing this guy just over here. 9 minus a negative 1 is going to give me 10 divided by 2. It looks like this is equal to 5. So that means that my average rate of change over the interval from 1 to 3 is 5. So that's pretty neat. I'm just going to clean up some of this space so I can go from here. So we found this part. Okay. All right. So we know our average rate of change is equal to 5. Let me just write that down. Okay. So our average rate of change is 5. Now, that was kind of a long process just to get to the mean value theorem part of this video, but let's actually draw this out first. So we found our first point. It was kind of around here. It was a 1, negative 1. That's what we found out when we found f of 1. Okay. So now 3, we went all the way up to 9. Okay. All right, so if we can think about this average rate of change as a secant line, kind of, that connects these two guys. So just like that. And we can kind of imagine it maybe just going a little bit further like this. Okay, so this secant line has a slope of 5. That's what we figured out when we found the average rate of change over this interval. So what the mean value theorem states, based on some certain conditions, which I'll get into in the future, but I want to I want our eyes on the prize before we get into the specifics of what has to happen. But if everything works out right, we can guarantee that at some point over the interval of which we're finding the average rate of change, at some point we're going to have an instantaneous rate of change or a tangent line that slope is equal. You can already kind of see that maybe, oh, it looks like right around here-ish, we might have a tangent line that's actually equal to the average rate of change on this interval here, which is pretty cool. But there's some things that we need to make sure are going on before we jump to this conclusion. So first things first, we need to actually let me hang on. All right, so our conditions for the mean value theorem, this kind of looks like a U. I promise it's a V for mean value theorem. So number one, we have to be continuous over the closed interval, okay? Of the average rate of change that we're doing. So it looks like we're going from 1 to 3 here. So this will be the conditions for mean value theorem just for this example, right? This interval can change. Okay, so first things first, we have to be continuous. We also have to be differentiable. I hope I spelled differentiable right. Now we have to be differentiable over the open interval. I ran out of space, so I'll just put it. Oh, I'll just put it here. 1, 3. Okay, so we actually only we actually need to be we don't need it to be closed over here. We just need to be differentiable over the open interval. Um, and you know what? That kind of makes sense because when we're looking at like the endpoints of what's going on here, it's hard to imagine almost kind of an instantaneous rate of change because we can't think of like what the limit is as we go that way. Anyway, it's not important, but uh, what's important to remember is we have to be continuous over the open interval, oh the closed interval, sorry, the closed interval from 1 to 3, and differentiable over the open interval. So keep in mind, if you're given like a problem, like a story problem or something, and they tell you, oh, okay, this function is differentiable over this closed interval or something. Remember that differentiability implies continuity because you can't be differentiable if you're not continuous over that interval. So if they just tell you that you're differentiable over a closed interval, you're set. That's all you need to know to apply mean value theorem. So let's see. Yeah, I'm pretty sure. Yeah, these are the only conditions for mean value theorem. Actually, now that I think about it, we just need to be continuous and differentiable. But let's think about why that makes sense, right? So if I have like for example, let's say I have I don't know. Let's go for like a rational function or something. Like oh, this might be like -1 or 1 over x or something. But let's think about like if we looked at like a secant line here, like this, and then to be clear, this is an asymptote right here. But and then we'll say, oh, mean value theorem states that at some point we have to have a slope that's equal. We have to have an instantaneous rate of change that's equal to um, the average rate of change over here. And you'll look for it. You'll say, oh, is it maybe up here? Oh, is it maybe down here? And you'll have trouble finding it, right? Because we're not continuous over our interval that we've chosen. And of course, if we're not continuous, we're also not differentiable over that interval, right? So uh, that's one example. If you see a function that's not continuous and you're asked to apply the mean value theorem and you're not continuous over that interval, you're going to run into problems. You're going to have to tell them that it's just not possible. Okay, so let's think of another example. So let's say I have like a sharp turn or something. So let's say I have like a absolute value of x function or something going on here. So and then let's try and apply mean value theorem. So I'm going to say, okay, my average rate of change is right here. Uh, an instantaneous rate of change with a slope that's equal to the average rate of change, and then you'll go looking for it. Well, I can't find one because right here we might be continuous, but we're not differentiable just right here on our interval because we have a sharp turn there. So that's kind of why these conditions are important to consider. Remember, uh, if it's not continuous or differentiable, well, I said or, if it's not continuous and differentiable, uh, if we can't followed these conditions, we just can't use mean value theorem. So um, let's actually inspect our function though. So let's actually look at what's going on here. Okay, first things first, are we continuous? Let's see. Well, I don't see any holes. Let's make sure there's not like any holes that are disguised or anything. So yeah, it looks like we're not undefined anywhere. We're not like dividing by zero anywhere. I mean, things are looking good. Um, yeah, it looks like we're continuous. So, uh, and a polynomial is gonna be continuous always, unless there's like something weird going on with it. So, yeah, so we're continuous. And then let's just double check in our minds that we're differentiable. And just looking at this, it looks like we are. If we wanted to be extra safe, maybe we'd just take the derivative using power rule stuff. Okay, 3x squared minus 4x. Okay, yeah, so I just got another polynomial, right? So polynomials never going to be undefined unless you're doing some weird stuff. You're like putting a, I don't know, like a rational thing in there somewhere. So yeah, it looks like we're good. We're continuous and differentiable. So based on that, we actually know that we're going to meet the mean value theorem, and we can say that the mean value theorem guarantees um, one, at least one. It can be more than one, but it'll be at least one spot, and in which we can actually uh, be uh, parallel. We can have a slope that is parallel to this guy, and it looks like we found it, right? We had one solution for this guy, and it looks like it's around here. Um, and speaking of that, let's actually find that. So let me take a moment just to clean up my screen so we can go through that. Okay, so I've kind of erased a couple things just so we got some more room to actually go through this. Just remember the conditions for the mean value theorem. We meet them, so we can actually use them in this case. And then I just erased some of the work for our average rate of change, just so we have some more room. So just remember that our average rate of change is 5. So, okay, so our first step has been met. We've actually concluded that the mean value theorem can be used in this case. So that's great. A lot of times they'll ask you, like, with the next step, you want to figure out at what x value you actually meet the mean value theorem. So we know that our slope is 5, right? So if we want to figure out the point that, if we actually want to figure out the exact x value in which we have this tangent line, so we can find this so we can find the solution for the mean value theorem, we can actually do this by, well, first things first, let's actually take the derivative of here just so we can reference that. That'll output the slope of the tangent line just around this line. So I've done this before, but let's go over it a little bit more slowly. So I'm going to do, remember that when I'm taking the derivative of something like this, I could kind of break this into smaller parts. So I'm just gonna only look at this guy first. So I'm gonna use power rule. I'm gonna bring down the 3 and subtract 1 to my power. So I'm gonna write f prime of x is equal to 3x squared. So I decremented my power, and then minus, and then 2x squared. So I'm gonna multiply my exponent and then decrement it. So I'll have 4x. So it's just some pretty basic power rule. Hopefully you're familiar with that. So anyway, so here, this is my equation that'll tell me where my slopes are. So if I want to find the solution to the mean value theorem, I can just find the point at which my slope is equal to 5, right? So 3x squared minus 4x. Okay, so this might get a little tricky, but let's see if we can go through it. So let's set this equal to 0, 3x squared minus 4x minus 5. Okay, I'm pretty sure this isn't something we can do crazy easy, so I'm going to quickly use a calculator just to find the exact point at which is going to be somewhere, it's going to be like just barely greater than 2, maybe like 2.25 or something, so I'm going to do that real quickly and then I'll come back. Alright, so I quickly just used Desmond to help me out with this guy. Remember, this is a quadratic, so we're going to have 2 solutions here, and this isn't a case where it would be imaginary, so don't worry. We have a negative answer and a positive answer. I'm only going to list the positive answer because that's... Oh, actually, no, I'm actually going to list both of them. So it looks like we have one x value that is negative 0.78. I'm just going to only go 2 decimal places here just for simplicity. Okay. And we have another x value, which is 2.119. Let's see. 2.119, that's like, I don't know, around here. That's kind of what we were thinking maybe where this would be. So these are my 2 solutions. In the case of this interval, though, we're not really going to be thinking too much about this guy because it's not on the interval we're interested in. So if you were to solve this problem like for an AP exam or maybe just a normal exam for a class, you'd probably only list this guy because it's the only one over this interval. Because usually when you're using mean value theorem, you're only interested in another tangent line over the interval here where you find the average rate of change. So I'm just going to kind of disqualify this guy. It's nice to know that we have another one, but that's not really too relevant for the context of this problem here. Okay, so well, let's move on. All right, so well, like I said, I graphed this function over on Desmos, and let's actually take a look at it in Desmos just so we can kind of see the mean value theorem in actions here. So the red line here, this is the function that we went over, x to the third minus 2x squared, all fine and dandy. So if we zoom out, we can kind of see what's going on. So this blue line, I've graphed the secant line that this is the average rate of change between x is equal to 1 and x is equal to 3 over our interval. So I went ahead and graphed it. I just used this form. Uh, and over here, I'm going to display a function that just literally gives us the tangent line to our graph over here. So as I change our A, you'll see that it kind of follows the shape of our graph over here. It's pretty cool, pretty mesmerizing. So anyway, let's actually evaluate like our solution to the mean value theorem just so we can see in action. So this is our average rate of change. So let's kind of go through the different x values that might have a slope that's tangent to that line that's equal. So it looks like here, oh look, right about here, looks like we have one solution to the mean value theorem, even though this isn't on our interval. If we expanded, oh, well, yeah, it's not really a solution to our interval because our interval was 1 to 3, so it would be from here to, 1 is over here. It would be from here to here. So this is kind of more like an honorary solution, but it's still kind of a solution. So uh, we have a case where our tangent line is equal, the slope of our tangent line is equal to the slope of our average rate of change line. So here's one solution, and then it looks like we're going, oh, now we're decreasing. Oh, now we're increasing again. And then right about here, oh, look at that. It looks like the slopes are equal now. So uh, there you have it. There's another solution to the mean value theorem. So yeah, if you're ever asked to use the mean value theorem, a lot of times they'll say, oh, see if the mean value theorem guarantees a certain c value in which f prime of c is equal to uh, like the average rate of change over a certain interval. First things first, what you're going to want to do is figure out, okay, can I actually use the mean value here, theorem here? So you need to be continuous over the closed interval and differentiable over the open interval. If they just tell you that it's a differentiable function for like all x or something, then you're good. You can use the mean value theorem because remember that differentiability implies continuity. You can't be differentiable if you're not continuous. So, and then if you figure out, okay, my conditions have been met for mean value theorem, from there, you'll find the average rate of change, which is uh, this guy over here. So this is the average rate of change. It's the secant line between these 2 points. And then from there, you'll take the derivative of this function, and then you'll set it equal to whatever the average rate of change is. In this case, it was 5 for us, so we set the derivative equal to 5, and then we solve for x to find our x values. And so, yeah. Um, And then once you figure out the x values, that's usually the end of the problem. So nice job, guys. You hopefully have learned mean value theorem. If you have any uh, other questions, if you don't feel very comfortable with it, there's plenty of resources out there. You can use Khan Academy. I'm sure there's a section on Khan Academy about that, and there's other YouTube videos. So thanks for watching, and I wish you luck on your future calculus endeavors.